Okay, it's a great pleasure to welcome Nima back to NYU. It's a special pleasure for me to introduce him since I was his PhD student. I think Nima requires no introduction for most of you. I'll just say he's worked on an incredibly broad set of questions in particle theory. He's come up with creative solutions to all of them, and he's been really influential in how our whole field thinks about a lot of our open questions. Let's see, among his many awards, he was one of the inaugural winners of the $3 million Fundamental Physics Prize. But more interestingly, he's also a movie star. Using the movie Particle Fever, which got the discovery of the Higgs boson. It's worth checking out. Notably for today, Nima was selected for this colloquium by our graduate students who requested him. And he asked them to choose the topic for the colloquium. So they were given 4 choices of topic. They voted. This will be the result of that. Well, that's all I'll say. I'll let Nima get started. It should be fun.
So it's always fantastic to be back at NYU where there's I have so many friends, and so I'm talking about this modest topic of what spacetime and quantum mechanics are going to look like in the 21st century, and I think it's a very good time to talk about this general subject because, of course, the understanding of spacetime and quantum mechanics were the 2 main revolutions that began the modern era of fundamental physics a little over 100 years ago. And it's very interesting today that we're still struggling to understand in the deepest sense what spacetime and quantum mechanics really are. And some of the biggest open problems on a large scale, the largest open problems in the field, all revolve around trying to understand that and potentially go beyond these 2 bedrock foundational ideas from the 20th century. This is a kind of a slogan of what we learned in the 20th century. We learned a lot of things, but I want to, the talk will roughly be structured in 2 pieces. I first want to substantiate this slide, or at least tell you the logical structure of this slide, because it's an incredibly important point. It's something that we didn't really even very fully well understand even 50 years ago. It's that this thing has become, I think, more and more obvious in the past 30 or 40 years to a theoretical physicist. But I think it's one of the amazing accomplishments of the 20th century is not only the understanding of these 2 big principles, relativity and quantum mechanics, not only the union of them in the structure of quantum field theory and the particular quantum field theory, the standard model of particle physics and of cosmology also that describes the fundamental interactions, but there's something more broad than that, which is that the very structure of these laws, the relativity and quantum mechanics themselves, are shockingly restrictive in what any possible universe could look like compatible with those principles. And that these 2 broad principles make the structure of the universe on large scales almost inevitable, up to very important details. But that's something that we couldn't say 50 years ago, but we can say now, and we really understand well now. So that's part 1, that these principles are incredibly constraining and make the structure of the world around us largely dictated. On the other hand, the main dramas of the 21st century is that we have reasons to believe that these 2 big principles need to be modified, or even more radically, replaced by things that are likely much stranger and further away from things that we understand today. So I think almost all theorists working in this field believe that space-time doesn't really exist. What that means, of course it exists. Time exists, space exists, all these things exist very usefully approximately, but that there are going to be approximate notions and not fundamental ones. They're not going to survive in the next description, in a better description of physics. In much the same way as the idea of a position and velocity of a particle, which is a bedrock idea of classical physics and is definitely approximately true, does not exist in quantum mechanics. And it's not a small modification of the quantum picture. We have to go from the words position and momentum to the words position or momentum. And that and or represents the magnitude of the conceptual revolution that had to be made, where we're in a similar situation with space-time today. Very likely doesn't exist. It has to be replaced with something else. That ultimately has to do with reasons having to do with gravity and quantum mechanics. It's even possible that we have to confront limitations of quantum mechanics itself. And this is a little bit more speculative. I think some people would not agree with this, but I strongly believe it. But not for stupid things. I'm not saying that quantum mechanics is modified in any dumb way that anyone experiment, anyone's lab is going to see practically. anytime soon, but that their fundamental mysteries show up when you attempt to apply quantum mechanics to the entire universe, or the universe that looks like ours, to cosmology, in particular to accelerating universes. And that makes it likely that we even have to understand quantum mechanics as emerging as something from something else. So the two bedrock principles that made the previous slide possible are both under question. So on the one hand, they're spectacularly successful. We have this amazing framework to build on that works. On the other hand, we have to remove them somehow in the next description of physics. This is a sort of situation that doesn't come along every day. Okay? It happens once every century or so, if you're lucky. And that's what the situation we're in. That this is the next kind of question that we have to try to confront. Closer to home, there's another very simple qualitative question, which is which may end up being related to the first one in an interesting way. We understand all these fancy, schnazzy things about the world. We can calculate the magnetic moment of the electron to 12 decimal places. But we don't have a good answer to the question, why is the universe big? Okay? Why do we have a large universe with big things in it? Of course, we can accommodate that fact in order to proceed and calculate all these schnazzier things, but we don't have a good understanding for why it is. If I say it another way, the first slide is possible if you take for granted that there is a big universe out there. You take for granted there's a big flat space-time out there, then these basic principles of relativity and quantum mechanics constrain the structure of things, but we don't understand how we got that situation to begin with. It seems very mysterious that we have a big macroscopic universe, which should be curled up to extremely tiny scales by violent quantum fluctuations, and it doesn't. Okay, so those are the questions, and now I want to spend a little bit of time explaining first the statement about the 20th century before moving on to the 21st. So this union of the picture of relativity and quantum mechanics, which was handed down to us already by the late 1920s, early 1930s, started being built, unified, just special relativity and quantum mechanics, into a theoretical structure that's called quantum field theory. And there's many ways of talking about what the quantum field theory is, but I'm going to emphasize the way that's most directly related to actual observations. Perhaps a little ironically, there's no fields fundamentally. Fundamentally, there's particles. The photon counters measure click, 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 click. So everything is fundamentally particles, but they're quantum mechanical particles. And quantum field theory is the structure that allows us to talk about the interactions of particles. And what we learned is that the interactions are incredibly simple. So electromagnetism is associated with this little stick figure interaction between electrons and photons. Gravity is associated with a similar stick figure interaction, three-particle interaction between electrons and gravitons. And the principle of locality is that these interactions take place at points in space and time. Okay? They're not at separated places. They take place at points in space and time. Again, we couldn't have action at a distance because of relativity. That would end up violating causality, right? So things have to take place at points in the space and time. What's remarkable, though, is that the interactions are the simplest possible ones, and then we concatenate them in all possible ways to get everything else which happens. So everything is reduced to these simplest possible interactions where three particles come together. Then we discovered the strong and the weak forces in the early part of the century, and it took a long time, the development of the Standard Model, until we realized that they're also described by exactly the same basic structure, the same stick figure interaction between three things coming together at points in space-time. Strong interactions between quarks interacting with the gluons, weak interactions between electrons and neutrinos interacting with W's and Z particles. And the reason it took so long is that we had to go to very high energies in order to see this fundamental similarity between all of the interactions. For something that from a fundamental theoretical point of view, going to very, very short distances is a detail, which is that the W particle, for example, is massive while the photon is massless. And the masslessness of the photon means that it can mediate a long-range force that you can detect. Of course, it dies off with distance in three spatial dimensions. It dies off like the inverse square law. The W particle is massive, and so it's much more difficult to excite it virtually out of the vacuum. And so it gives you an interaction that dies exponentially with distance, which is why it's so weak. It's why a neutron lasts for 15 minutes in outer space before it decays. 15 minutes is a gargantuan timescale relative to any timescales associated with the itty-bitty neutron. And it's doing that because it needs to excite this very difficult to excite virtual W particle to trigger the conversion. So the range of the weak interactions, the Compton wavelength of the W particle is around 10 to the minus 16 centimeters, so we had to go to around 10 to the minus 16 centimeters. The energies that correspond to energies 100 times the mass of the proton in order to finally see that this is what is happening. And that was the hard-won lesson from the 20th century, is that this basic unity of the interactions of elementary particles and of the laws themselves are seen by going to very high energies. That's why we go to high energies. Not so much because we care about the building blocks of matter. I don't know too many people, too many colleagues who care that much about the question of the building blocks of matter. We go to high energies because we care about the structure of the laws, and we learned that the structure of the laws can be hidden, masked by accidents at long distances, and you only see them nakedly and cleanly at short distances and high energies. Okay, and so it's always the same. It's always these little stick figure interactions. Another feature is that particles have spin. So electron has a spin 1/2, the photon has spin 1, the graviton has spin 2, the W particle has spin 1 in units of h bar. Quantum mechanics tells you that the spins can be a half integral multiple of h bar. But just the laws of quantum mechanics would allow particles to spin 17 halves, or 99. Okay? And yet the fundamental elementary particles that we see only come from a tiny menu of possibilities. Okay? These are the familiar ones. So at this point, you can ask two questions. So that's just what I said. The particles we see are incredibly simple. And this is the particular menu of possibilities of particles that goes into the standard model. Okay, so slightly complicated. We have particles of different types, and we have particles of spin 1 and spin 1/2, and we have the graviton of spin 2 with a particular pattern. It's not the simplest thing. It's definitely not the most complicated thing. But what matters more than the structure of the menu is just that it's all the same thing. It's always these three-pronged interactions with this tiny menu of possibilities. So now you can ask the question, why did it end up being so simple? It could have been much more complicated. Why is it that we see only these stick figure three-pronged interactions and nothing else? Why don't we have, I can't count there, why don't we have like 12-pronged interactions? That would be a disaster if we did, right? Because then it would be hard to explain complicated things in terms of simpler processes. You'd have to have a fundamental 12-particle interaction and more complicated ones. Okay? And yet everything can be boiled down to these very, very simplest ones. So are we just lucky that somebody loved us to make this possible so we can understand the universe? That's one question. Another question you can ask is, why is there such a tiny menu of spins? Why don't we have these fundamental elementary particles of spin 77 halves? Okay, why is it just drawn from this small menu? So these are two qualitative facts about the world, apart from the specific particle content we see in the standard model. And this is the thing which has a beautiful answer. Okay? And is what I was advertising in the very beginning of the talk, which is that we now know enough about the way the world works, both relativity and quantum mechanics. This is not a statement we could make with just one or the other. We need both. But with both relativity and quantum mechanics, you can do the following thing. You can lock up a bunch of sufficiently competent theoretical physicists in a room and not show them the world outside, which is a little counterfactual because they're in a room which is in a world and so on. Never mind. Okay? So lock them up in a room. They don't see the world outside. You just hand them laws of relativity and quantum mechanics and food, graduate students, everything they need, paper. Okay? And you say, go. What can the world possibly look like compatible with these principles? Now, they also have to be sufficiently competent. So, for example, if you gave me this exercise, I would look at it for a week and I would say, sorry, it can't be done. Just can't do it. Okay? Now, by the way, why can't it be done? What's the nub of the problem? Just because it's a very simple one. It's because relativity changed a lot of things. It made space and time, it united space and time. Okay, but it didn't change the classical nature of physics. Quantum mechanics changed a lot of things. Things aren't deterministic. But it loves a picture where you specify the state of a system at one time, and then you evolve to another time. Okay, so time is very special. So relativity, time is not special, I'm classical. Quantum mechanics, I'm not classical, time is very special. The two structures do not speak the same language at 0th order. So it's not trivial to put them together. And that's why I would say it can't be done. But if you think harder and you set up the question very physically, you eventually discover the following thing. Whatever the underlying theory is, we don't know what it is. But whatever it is, if it's compatible with these two principles, at long enough distances, you will discover that the particles can only interact with these stick figure 3-pronged interactions. There may be other interactions with 4, 5, 12 prongs. They might even be there, but they will not be important. They will not be leading things to describe the physics at long distances. So the only things that you need to dominate the physics at long distances is this basic one. And the only spins that are allowed for the particles to have, fundamentally, at very, very high energies, very short distances, are 0, 1/2, 1, 3/2, and 2. Okay? And that's it. So this is quite interesting. So particles of 1/2, 1 are the familiar ones: electrons, photons. The spin 2 is a graviton. Oh, these guys would tell you, by the way, this spin 2 guy is very weird. It's very special. You can only have one of them. You can't have two. You can only have one, and it does the following thing: if there's massive particles around, it makes them go around in orbits. Okay? They've never heard of gravity. There's no falling elevators. They're not Einstein, but they don't need any of that. They just need quantum mechanics and special relativity to derive all the consequences of general relativity, for example. So, quite opposite the usual perception that general relativity is a bigger deal than special relativity. Is the other way around. General relativity is a special case of laws that are compatible with both quantum mechanics and special relativity. Okay, these other guys have, so these guys are also pretty special. You can have at most 8 of them, these 3/2 guys. They're interesting. You can have a bunch of these guys with their very specific interactions, a bunch of these guys, any number of these guys. And anyway, there's some rules for how they all can talk to each other. And so all you have to pick a menu of these guys and a set of interaction strengths for that, and that's it. That's all the choices you have. So we boiled down from a continuous infinite set of possibilities you could imagine. You imagine the evolution that we've made. If you're a Newton, it could have been 1/r² or 1/r to the pi. And it makes no difference fundamentally. You just choose the one that matches nature. And we've come to a point to take a continuous infinity of possibilities down to a discrete little set, a small menu and a small set of interaction strengths, just as a consequence of relativity and quantum mechanics. Now, unfortunately, if I yes. Huh? The masses is the entire, that's exactly where I'm coming to in a second. So this is all in the approximation where we ignore the masses of the particles. We imagine we go to very, very high energies and we talk about, we talk about the interactions of massless particles.
So how do you define long distance?
Just very high energies relative to the masses of any particles you have.
Right.
So,
you need the mass.
well, so that, yeah, well, no, not indeed, if you have any masses, then you go to you have to go to a regime where kinematically you can ignore the masses of the particles. Now, it would be a whole other nice colloquium to explain why that last statement is true. So unfortunately, I'm not going to be able to do that without Josh and/or Greg killing me. What I'm going to do is just assert it, but at least. Just so you know logically that it's true, and also now tell you how it connects with the story of the Higgs, because that's nicely related to the question that was just asked. There's only one footnote to this story. The footnote to this story is that what nails everything is the assumption that the particles are massless. Okay? And you say that can't be a bad approximation. Whatever masses they have, in the limit when the energies are incredibly high compared to the masses of the particles, surely you can ignore their mass. And you can treat the components as massless. Okay? So this is a good approximation to the fundamental short distance physics, and then something happens at long distances. However, there's another qualitative fact about relativity and quantum mechanics, which is an important distinction between the number of degrees of freedom that massless and massive particles have. So while you think that you can ignore mass as you go to very high energies, and it's kinematically true that you can, if the energies are much larger than the mass, there's something that you can't ignore, which is this. There's a discontinuous difference between something moving at the speed of light and something not moving at the speed of light. Okay? Something not moving at the speed of light you can catch up with and put to rest. And that means that the number of spin degrees of freedom for, let's say, a massive spin 1 particle is 3, because however it's spinning, you catch up with it, and then you rotate your head and you see that it can spin in any number of 3 directions, whereas you can never catch up with a photon, so the number of massless degrees of freedom is 2. That 3 versus 2 is the entire drama of the Higgs mechanism. Okay? But just from the point of view of this story, it tells you that, there's a little catch. As you go to very high energies for particles with spin, like the W particle, you can't just ignore the mass because there's some extra degrees of freedom there. So what you have to do is you have to take the massive degrees of freedom you have at very low energies, extrapolate them to very high energies, and be able to reassemble all the degrees of freedom you had at low energies into these consistently interacting massless ones at high energies. Then it turns out to be just a very simple counting problem, that 3 is not equal to 4, as it turns out, that you simply cannot do it. If all we knew about were the particles before the Higgs, there was just a mismatch. You could not reassemble the particles that we knew at very long distances, at low energies, into ones that made sense into this allowed rubric of massless particles at high energies. There had to be an additional degree of freedom. Now, a priori, there could have been 1, there could have been 50, there could have been tons. The physics would have changed in a radically different way. The incredible thing is that all it took is 1. A single, solitary, new degree of freedom, that's the Higgs, and that allows you to smoothly interpolate now between massive particles at low energies and massless particles at high energies. Notice in this story I haven't said anything about symmetry breaking or Mexican half potentials or any of those things. And that's because those things are all metaphors. They're all description-dependent statements about the physics. They're not properties of the actual physics itself. I guarantee you in 200 years, no one will be talking about the Higgs mechanism drawing these little pictures like that. Okay? But they will talk about it like this. But this is actually true. So the other thing is an artifact of a particular way of talking about the physics. It doesn't reflect a feature of the physics itself. All right. So now, what's of course very interesting here is that the Higgs was discovered at the LHC. Colliding particles with energies roughly 10,000 times the mass of the proton, velocities 0.79 times the velocity of light, probing distances 1,000 times smaller than the atomic nucleus, and they discovered the Higgs. Okay, so they discovered this particle. So it was obviously a triumph for experiment. It's a triumph for theory, and it shows that these basic principles actually work, that this belief in these principles paid off. Why do I say that? It's because we knew there was a mismatch. You could just, by this counting argument, you could see the number of degrees of freedom was wrong. You had to add something if you wanted to go to higher energies relative to lower ones. So this is a very interesting opportunity you have when you have to change something, because you have to go and see what's allowed by the principles you have already. And it was interesting that nature had not chosen to use, as far as we know, elementary particles of spin 0 before. That's exactly the thing that was needed to potentially solve this problem, and it did solve this problem. Okay, so we got to change that red 0 into a black one, and that's why the Higgs is so interesting. It's the first really new particle that we've seen. It's the first elementary particle of spin 0, and that fact is associated with a lot of mysteries that I'll come to. But okay, this basically closes the story of the 20th century. With the discovery of the Higgs, I would say the 20th century in fundamental physics began early in 1895 with the discovery of radioactivity, and it should have ended in 1999 in Waxahachie, Texas with the discovery of the Higgs particle, but it ended in 2012 in Geneva with the discovery of the Higgs particle. And that's the end of the one arc of development of 20th century physics. Now, for the first time in our history, we do have a self-consistent theory that doesn't predict its own demise. It can be self-consistently extrapolated to exponentially higher energies than we have. And eventually it breaks down when gravity becomes important and things that we'll talk about in a second. But we have something that's not crying uncle, okay, nearby. The theoretical structure is robust, and this whole set of principles works and makes sense. All right, so now let me move to talk about the 21st century questions. So the first one is associated with this slogan, that space-time has got to disappear somehow, and we don't yet know what replaces it. So there's many thought experiments that show you that we have to lose the idea of space-time eventually. Here's one of the famous ones. Let's say you want to examine some region of space. Just look at it and see what's there. And now, because of quantum mechanics and the uncertainty principle, we know that to probe shorter and shorter distances, we need higher and higher energies. And that's why we ask larger and larger multinational governments to build more and more expensive accelerators in order to do so. Okay? But in principle, if you want to probe arbitrarily short distances, there's no difficulty. You just need arbitrarily high energies. However, something new happens when gravity is involved. That's because at some point you put so much energy into such a tiny region of space that you collapse it into a black hole. And so then it blocks you from seeing what's going on in there. Exactly what you wanted to do to probe what's going on at very short scales, you're obstructed by doing that. If you get frustrated by this fact and you build an even bigger energy accelerator, what happens? You make an even larger black hole. Make it even harder to see what's going on at short distances. So this means, incidentally, that the basic idea of reductionism, the most fundamental idea of reductionism, that we have to go to the shortest distances and that's where all the action is false. Okay? We know that already. At least when we get to these scales, it's false. Higher energy starts turning to longer distances again. Okay? But something more dramatic is true, that there's simply no operational way of talking about distances and times that are on the scales where this happens. Now, the scale where this happens is the famous Planck length, around 10 to the minus 33 centimeters. Its tininess is just a reflection of how weak gravity is compared to all the other interactions. And this scale is hopelessly removed, of course, from anything we can probe directly experimentally. There are other aspects to what's going on near the Planck scale and what the difficulty is. For example, if I look at the ratio of this electric to gravitational strength between two electrons, of course, famously at long distances, it's 10 to the minus 42. Gravity is very feeble compared to electromagnetism. You would think they're both inverse square law forces, so the ratio stays constant. That's true until you get to around 10 to the minus 11 centimeters. That's the Compton wavelength of the electron. Past that point, just trying to shove the electrons closer and closer together costs uncertainty principle energy. That energy gravitates and it makes the gravitational attraction go up, even though the electric force stays the same. So this ratio actually starts climbing. Somewhere around 10 to the minus 31 centimeters, they catch up with each other. And at 10 to the minus 33 centimeters, gravity is overwhelmingly strong. Okay? That little gap between 10 to the minus 31 and 10 to the minus 3 is the fine structure constant, 1 over 137. And that reflects the fact that the electric force is a little bit weak already, okay? But not so terribly weak. It's associated with a small interaction strength around 10 to the minus 2. Okay? But eventually, when you get to 10 to the minus 33 centimeters, gravity is just overwhelmingly strong. Here's yet another aspect of the problem, many aspects of the same problem. And this is only one, and not even the deepest aspect of putting together quantum mechanics and gravity, but one of the first ones that catches your eye. So what happens, again, the world is quantum mechanical, so what happens when I collide electrons at very, very high energy? So gravity is going to be important. And there's some probability amplitude from exchanging gravitons, just from gravitational scattering. Now, just from dimensional analysis, you can see that that probability amplitude has a g Newton in front of it and has to grow with energy. So this is like g Newton mm, except the m is like energy. Okay? So this probability amplitude is getting larger and larger. And so at some point when the energy gets comparable to around this 10 to the 19 gigaelectron volt, the amplitude becomes comparable to 1. Okay? Then you're in trouble. When the amplitudes are comparable to 1, it's nonsense. When you mod square them and add them all up, they have to add up to 1. They can't become comparable to 1 or bigger than 1. Okay? So this is another example. It's just a concrete, we can imagine an experiment. We can't do practically, but we can certainly imagine it, where scatter electrons at an energy 10 times m Planck, the Planck scale. What happens? We don't know. Nothing in our current understanding, despite the fact there's stick figure into all those things that I said are wonderful and they all work, they do not allow us to give a physical answer to this question. All right, so now there are other situations where we don't understand things. When the curvature in space and time becomes comparable to the Planck scale, again, we have no idea what's going on. So when we extrapolate the universe back earlier in time, there's the time when the curvatures become comparable to the Planck scale. That's what's colloquially called the Big Bang singularity. And then often asked questions by lay people is what happened before the Big Bang. Well, what's going on is near the Big Bang, the words happened start being fuzzy. We don't know what time and space mean around that point, so we don't even know if the question is well posed. And so what is the well posed question? We don't know. Similar issues happen when you fall into a black hole. The inside of a black hole is a lot like a collapsing universe, and you have the Big Crunch analog of the Big Bang singularity on the inside of the black hole. And in all these cases, there are situations we can ask questions that we simply don't know how to answer. So our theories just break down when gravity is strong and quantum effects are dominant. Okay? So this is very clear. Even though we can't do the actual experiments, we can do thought experiments that we cannot give the answer to. And it involves questions about gravity and quantum mechanics at Planckian distances, at least in the simplest manifestation. Now, I want to spend a little bit of time talking about how we can go about confronting questions like this as theorists. In order to give you a somewhat more accurate picture than some of you might have of how work in this business is actually done. Because you might have the impression, since the phenomenon here is associated with the Planck scale, no one's going to build an accelerator to go near the Planck scale, then it's all pure speculation, right? You're just sitting around as theorists making up stories, nymphs and dryads and leprechauns around every corner. And you're not going there anytime soon. Yes, of course, we all agree experiment decides what's right and wrong. We're all scientists. But pragmatically, no experiments are going to be done there in your lifetime. It's a good job if you can get it just sitting in your armchair theorizing about things that you're never going to be ruled out about one way or the other. Okay? And this is extremely false. It's so far from the actual truth. Would that it was so, we would suffer a lot less in this business. And I want to explain to you why. Okay? And it's a very important corollary of what I told you before, that the principles of relativity and quantum mechanics are shockingly predictive, are shockingly restrictive. They come from experiment, ultimately. Okay? The relativity and quantum mechanics are true. No one would have dreamed, certainly, quantum mechanics up. They come from the soil of experiment. But now we know them as principles, and being compatible just with the old things that we know is so difficult that it's almost impossible to come up with candidate ideas that might be right. Never mind that are right, that we then have to go compare with experiments to decide. Okay? So, in other words, what I want to do, and this is an example par excellence, because it's a question involving things near the Planck scale, and you might think that you could come up with a million different possibilities for what's going on near the Planck scale. And okay, you like this one, that one looks pretty, you like this, your friends like that, and it's like that it's sociology that decides which one is interesting and which one isn't. And in fact, it isn't. It's experiment that's guiding us to which ones we're focusing on. But it's not new experiments. It's all the century of old experiments that established relativity and quantum mechanics to begin with. Just being compatible with those principles is so difficult that even finding one example that works is something that's worth following up on. And I want to just use the next few minutes as a little vignette to illustrate this process. So here's the first challenge in quantum gravity. We just talked about the problem that you can collide electrons or gravitons at very high energies and the amplitudes become big, right? So there's a well-posed challenge. There's an amplitude. You don't need to look at these symbols. I'm just writing it just so I write a completely precise, correct formula. So you see these things are very concrete and they're simple. Okay, so here's a concrete formula. These funny brackets are just something that tells you about the polarizations of the particles. And the whole thing goes like a power of energy squared. That's just what we talked about before. That's what the answer is supposed to look like at very low energies. But as we said before, it's wrong at high energies. Wrong at high energies because the amplitudes become bigger than 1. So now you have an opportunity to play a game as a theorist. You say, okay, I want to fix it. I'm going to make a guess. So I'm going to make a guess for what the actual amplitude could be. In the real world, it's something, right? I'm going to make a guess for what it could be. And here's what I'm going to do. This is what it is at low energies. I want to write down a factor that just kills it, makes it smaller as I go to high energies. These S and T and U are just a measure of energy. So as they become they're units of energy squared. So when they become, I just write down some factors like this that are small, become 1 at low energies, but just kill it at high energies. Okay, so I just write down some simple modification, and I just wrote it down to look like that, just to mimic the little structure that we saw down there. I didn't mention it, but you could repeat the similar exercise with the problems in particle physics that we were dealing with before the Higgs was discovered. And if you did exactly the same game, you did exactly the same game, you would have written down the correct answer, the Higgs. Okay? So this game succeeded. This is previously has succeeded. So you try it again here. Okay? So you say, great, I'm done. Okay, I'm done. And now you say, no, but I don't like that one. I want to have 6 factors here. Sure, that's yours. Okay? And see, if any of these things were fine, if any of them were consistent, then this would be a pointless subject to think about. Okay? Because the only way to tell them apart would be to do experiments at the Planck scale. And until you do that, okay, they're all just guesses. So this is the typical journey in the career, or the day or the career of a theoretical physicist. Is you begin, there's a problem, there's a famous unsolved problem, and you think it's easy and you solve it. Okay? And then you look at it. You say, oh, was I really right? I have to make sure that this is compatible with all my principles. And one of the principles of quantum mechanics is that when amplitudes become large, so you see here, when s becomes close to m squared, this amplitude formally has a divergence. It has a pole. Okay, but those things have interpretations. They're resonances. Okay? So we can have amplitudes becoming large, but only when what were virtual particles become real. Okay? So they have to have a consistent interpretation in terms of producing and decaying some intermediate particle. And that puts some restrictions on what the sort of coefficient of this divergence is. It has to be positive in some appropriate sense. If it isn't, if it's not positive, it's negative, then that means that there's negative probabilities, and this doesn't make sense. Okay? So you try that on this example, and you find that it's negative. Okay? When you try it on the Higgs example, it's positive. It's great. You try it on this example, it's negative. You say, oh, maybe I screwed up. I tried some other factors. No, every one of them is negative, negative, negative. After a little while, you prove a theorem that no matter how many finite number of factors, whatever ratio of polynomials you write down, always it's negative. There's something which is negative. So again, it's a typical evolution. You go from thinking the problem is easy to thinking the problem is impossible. Okay? And then somebody comes along with this formula. Okay? So it's exactly the same thing, the same basic thing, except instead of those factors before, we have these gamma functions. Now, I'm just writing it down so you see again, it's very concrete, very, very concrete. The gamma function, to those of you who don't know, is just the factorial, but it's a definition of factorial that makes sense even for non-integers. Okay? So somebody wrote down this miraculous formula. Now, why is it miraculous? Because for this formula, when you go check to see, are those probabilities negative or positive? They're all positive. That's a total miracle. You check, every single one is a positive. Now you say, I have no idea how this person got it, but now I know the trick. I made these gamma functions. Now surely I can do 15 million other things around it. No, you touch it with anything else now, and you screw it up again. There's something negative, right? So now where did this come from? This is roughly the way the history worked. It's not quite. It's a little slightly different, but it's not far from the way the history works. Physics isn't about miracles. It's just that you have to get lucky sometimes. When you have very hard problems, you're searching around. Sometimes you stumble into something great. But the point isn't to keep gawking at its miraculousness. You have to understand where the miracle came from. And when people studied this formula for many years, they eventually, 4 or 5 years, they eventually realized that what this formula was telling you was the amplitude if you imagined that the particles weren't little points but were little loops of string. Okay? That's where string theory came from. And that string picture is what explains where these funny gamma functions come from, and of course a whole host of other things. It's the physical picture of what is actually going on. But I'm telling you the story in this way because it's kind of the opposite of the way that sometimes string theory is talked about, right? Normally, you say, one day people have the idea, instead of points, things are little loops of string. I can tell you when I was in grade 6 and I read a Scientific American article about this, I thought, these guys are lame, right? I mean, I could have thought of that. Anyone could have thought of that. But maybe they're little membranes instead. Maybe they're little, fractal shapes. There's 5 million things it could be. You like strings. I don't know why. It doesn't seem so deep and important. And that's because, because it's easier than this more tortured story. But the more tortured story tells you something much deeper about it. There's something singular and unique and rigid about this structure. And it's this rigidity that is a huge guide to us because that's what we're up against, right? Just trying to be compatible with relativity and quantum mechanics is so constraining that if you find one example, you pay attention to it. In the 50 years that people have been trying to write down formulas like this, nobody has come up with another formula. I can tell you the rules. I can tell a high school student the rules. And if they come up with another formula that satisfies the same rules, you will be a superstar in theoretical physics overnight. Okay? It's not about clubs and who likes who and so on. It's because there's a formula. And the formula has this miraculous structure in it. And after you study it, you see this miraculous structure comes from this assumption, and so you keep studying it. Okay? So it's not sociology, it's experiments that are guiding the things that we study. Now, this is by now understood to by far not be the deepest and most important thing about string theory. The subject has evolved a lot. That's what was exciting about string theory in 1985. The subject evolved a lot since then. And in fact, calling it a theory of strings is just one small aspect of this larger structure, which tells us how to put together quantum mechanics and gravity, at least in a few situations. Maybe the most important thing that happened in the subject in the last 20 years is an instantiation of this basic idea that we have to see space-time emerge from more primitive ingredients. There's a very important basic fact about quantum mechanics and gravity. If you try to make a measurement of some property, let's say in this room, and the world is quantum mechanical, so in order to get any precise numbers out, you have to do an experiment infinitely many times because it's probabilistic, and you have to do it with infinitely large measuring apparatuses because any finite size apparatus will on long enough timescales suffer its own quantum mechanical fluctuations and have unavoidable errors associated with it. So it's a basic fact of life about quantum mechanics that precise observables, and precise observables are useful to focus on because they might be what a real theory is about. Precise observables need you to drag around these infinitely large apparatuses with you everywhere you go in order to make, in principle, perfectly accurate measurements. In a world without gravity, that's not a problem. But gravity doesn't like that because it's universal. And even the apparatus gravitates. And if you try to do an experiment with an infinitely large apparatus in this room, you can't do it because by the time you make the apparatus bigger and bigger, it becomes so massive that it collapses the whole room into a black hole. And then you can't do the experiment, okay, perfectly accurately. So it's a fascinating fact about gravity that was understood by people who thought about it deeply already in the 1960s, that the only things that we can talk about in a quantum mechanically precise way about gravity involve experiments that you can't do on the inside of a space-time, but you have to take to infinity. Okay? You have to take the measuring apparatuses out to very, very far away, where you can make them big. They can fire particles into the interior of the space. They can interact with each other in some way and come back out, and you can measure their properties. So that's something that in other guises you may have heard of associated with the words of holography or the holographic principle. Sometimes it's thought of as a very modern idea, just that qualitative observation. But again, that qualitative observation goes back to the 1960s, people like Bryce DeWitt and Roger Penrose. But what is more amazing is that the observables live at infinity. And since the observables live at infinity, it's possible that there's another way of computing them, which never talks about the inside. You know, the experiment starts and ends at infinity, and so it's not crazy that there might be some way of describing how to get the answer by a theory that only lives on those walls at infinity. That's a new idea. Okay, that is a new idea. That's an idea that came out of studies in string theory in the late 90s. In a particular kind of space-time. And it's a particular kind of space-time that kind of looks like the world inside a box. Now, in gravity, you can't just make boxes because everything is sort of fluctuating. So you have to come up with a warped geometry, which effectively acts like a box. And these negatively curved spaces, known as anti-de Sitter spaces, are exactly like that. So they have negative curvature. Now, the curvature could be 10 billion light years. So if we didn't know about cosmology, we couldn't tell that we don't live in anti-de Sitter space. Okay? All of the short distance properties are exactly the same as they are in flat space. But by making it have this negative curvature, you can effectively make it be like the inside of a big box. Even though the distance out to the wall is infinity, light takes a finite amount of time to go and bounce off of it. So it's the closest you can come to putting gravity in a box. And the amazing discovery that was made is that you could either think about processes where you ping things on the outside of the box and things going to the interior bang into each other and come back out. And in that description, there's an extra space directions, there's gravity, strings, all the rest of the stuff. Or you can do a calculation involving a completely ordinary theory of particles, a more strongly interacting and more supersymmetric version of the ordinary theory of strong interactions that we know, which lives on the walls of the box, and they give you exactly the same answers. So that means that string theory and particle physics are conceptually identical things, and there aren't these different camps in theoretical physics. There's one large animal, which is the structure that knows about relativity and quantum mechanics at the same time, and is consistent with both of them. And we're slowly by slowly learning more and more about it. One of the amazing things is that what seemed like radically different starting points end up being related in these very surprising ways to each other. So this, as I said, is probably the most important theoretical development of the last 20 years. But it's a baby step towards the idea that there is emergent space-time. And the reason it's a baby step is that it's only space, this interior part, which is emergent. The time that flows on the outside is exactly the same as the time that flows in the interior. And so that's related to the fact that this space-time does not look like ours on large scales. It's not cosmological. It doesn't have an origin. It doesn't have evolution. And that's where the hardest problems lie. So, and in particular, in our accelerating universe, I probably don't have time to explain why the accelerating universe makes life much harder, but we don't even really know what the meaningful physical questions to ask are, which are precise. We can ask all sorts of approximate questions, but the questions that quantum mechanics allows us to ask precisely, we can't ask. Maybe I'll say it very quickly. It again has to do with this weird fact about, but well-known fact about quantum mechanics, that in order to make precise measurements, you need infinitely large apparatuses. It's a funny fact about the quantum world. You have to separate the world into pieces. The system that's being looked at that could be finite, but an infinite rest, an infinite thing which looks at it. And in an accelerating universe, we have only access to a finite amount of stuff, because there are regions of space very far enough away, light from them can never make it to us. What we see is what we get now in the universe, and it's finite. It's enormous, but it's finite. And that fundamental finiteness is in deep conflict with quantum mechanics. Quantum mechanics needs something infinite in order to make sense. And this is why we don't know what quantum mechanics means in an accelerating universe. It's one of many conceptual difficulties here. This is probably the very hardest problem in physics. And that's because it involves a notion of emergent, not just emergent space, but very likely emergent space-time, because it's cosmological, and perhaps some extension of quantum mechanics to deal with it. All right, so that's the set of questions having to do with emergent space-time. And now I have a speculation here, which, given time, I probably won't elaborate on. But my own belief is that we'll eventually come to see that quantum mechanics and space-time are not I mean, right now we think of them as sort of two separate things, and then we do what we have to do to jam them together. One theme that's emerged in the last 20 years because of this correspondence between string theory and particle physics that I mentioned is that maybe quantum mechanics is king, and that the space-time emerges from various properties of quantum mechanics. Recently, there's a lot of exciting work on trying to understand on seeing how the intrinsic quantum properties of entanglement are related to the emergence of space. But I suspect that something more radical is going on, and that we're going to see that the quantum mechanics and space-time are not, one is not more fundamental than the other. There's more primitive building blocks, and they will emerge hand in hand, sort of joined at the hip, impossible to separate from this more primitive substrate. Now that seems completely vague and abstract. The next 5 slides were meant to give a little bit of evidence for that, but I don't have time for it, so we'll move on to the next subject. All right, so now I want to talk about the second set of questions. Why is there a macroscopic universe? And here, one aspect of the problem is, so notice that in the previous discussion, even in the first part of the talk, we had to assume that there was a big space-time out there, that there are particles moving around in the space-time, and relativity and quantum mechanics dictated how they interacted. But you have to put in the fact that there was this big world, and they were moving around in it so they could interact at points and so on. If the world was curled up to ludicrously tiny sizes, it wouldn't make any sense, right? So you have to give that assumption to begin with. What's amazing is that on the one hand, that assumption is so constraining it leads to all these correct things. On the other hand, we have no idea how that initial condition, if you like, emerged to begin with. And one aspect of the problem is that there should be an enormous amount of energy in the vacuum. So we know that in quantum mechanics, even lowest energy states have some non-zero energy of order Planck's constant times the relevant frequency of oscillation. So if you look at the energy in vacuum quantum fluctuations, if I take a little box in space, there's some typical size vacuum fluctuations whose wavelength is the size of the box. So as I make the box smaller, the wavelengths become smaller, the frequencies become larger, the energy is larger. So the amount of quantum fluctuation, energy in the quantum fluctuation is larger and larger in smaller and smaller boxes. A total disaster. There's an enormous energy density. just from these quantum mechanical fluctuations. And we can estimate how big it is. We can't make this box arbitrarily tiny because eventually space-time is doomed, blah, blah, blah. So when the size becomes comparable to the Planck length, we have to stop. But if we stop before we get there, just to get an estimate, we get roughly something that's a Planckian energy per Planckian volume. And that energy density is enormous. We don't have to do any calculations to figure out what that energy density would do to the universe, because there's only one word appearing everywhere here, Planck. Planck density, Planck energy, the Planck scale associated with gravity. So this would curve the universe with a curvature scale of order the Planck scale. So it would either make it negatively curved with a curvature radius of order 10 to the minus 33 centimeters, or it would make it explosively grow, double in size every 10 to the minus 43 seconds. This lambda is the energy density in the vacuum, sometimes called the cosmological constant. So we've just done an estimate for the cosmological constant, and a prediction that the universe should double in size every 10 to the minus 43 seconds. And that prediction is wrong by 60 orders of magnitude, because the universe doubles in size now every 10 billion years or so. So this is not something that we're proud of. Okay? It's the biggest, I used to call it the biggest disagreement between theory and experiment in the history of physics, but that's slandering other fields. I don't think anyone has made a bigger mistake, ever, in any field. Okay? It's a huge discrepancy. And this is from a field where otherwise, in other contexts, we calculate things to 12 decimal places and we agree to experiment. Okay, so what do we do? So the most basic fact about the world before these fancy things like the G-2 of the electron is that it's big. So what do? We say that, well, there must have been, in addition to this quantum correction, a classical piece of the vacuum energy sitting there already, and that they just happen to cancel each other. Okay? So, and if somebody calculated this to 120 decimal places, you say, thank you for your hard work. Well, this must have been negative that thing to the same 120 decimal places, and starts to disagree in the 121st decimal place. Okay? Now, there's nothing wrong with this. Okay? Okay? There's nothing logically wrong with this. And it's unlike the other problems that we talked about before. It is unlike the problem of quantum mechanics and gravity. There's something really wrong. I mean, I don't know how to predict what happens when I collide gravitons at energy 10 times m Planck. Here it's not like that. Here I can do this. In fact, we implicitly do it. And then we get along with our lives, right? Then we calculate other things and everything else works. There's nothing wrong. But it makes us feel that we're missing something big. I mean, it's not a small little thing. This is it's not a small detail discrepancy. We don't have a good answer to the question why the world is big. There are these humongous vacuum fluctuations, violent, more and more violent, shorter and shorter distances. So why is there a big macroscopic coherent universe? Okay. Now, there's another aspect of this problem associated with the Higgs. Okay. Let me phrase it in it's exactly the same thing, but I'll phrase it in another way. The masses of all of the elementary particles are very, very small compared to this Planck scale, right? That's, again, a reflection of how weak gravity is compared to all the other forces. And you can ask, why is that? Why aren't all the scales closer together? Okay, if all the scales were close together, you and I, we'd all collapse into black holes. There would be no love, it would be a very sad universe, okay? But it's not like that. There's this huge separation between the scales. So you can ask, why is that? Is it reasonable that we have, again, these big violent quantum fluctuations? Is it reasonable that we have these large separations of scale? And so do we understand, for example, why is a particle like the photon massless? Why doesn't it have a big mass compared to the Planck scale? And here, there is a beautiful answer to the question, which involves, again, counting on your fingers. It makes sense that the photon is massless because 2 is not equal to 3. Okay? You imagine in some approximation, the photon, let's say if it didn't interact with anything, it would be a massless spin 1 particle. Now let it interact with all the virtual quantum fluctuations in the vacuum, however you like. It can't all of a sudden become massive, because if it did, this number of degrees of freedom would have to jump discontinuously from 2 to 3. And that can't happen. Okay, so for particles that have a spin, we can understand how they can emerge, and their emergence is robust. This is, by the way, also why it is that when our condensed matter friends engineer in labs all kinds of exciting and interesting materials that have good descriptions as effective quantum field theories at long distances, they can engineer in the lab naturally from fancy enough materials, but they don't have to monkey with the material once they find the right fancy one. They can engineer all the kinds of particles that we see in the Standard Model. We can see things like photons, we can see things like quarks, okay? And that's because these particles with spin are robust. Their existence is robust because of this discontinuous difference in the number of degrees of freedom between massless and massive. But the Higgs is different. The Higgs has spin 0. And the number of degrees of freedom of a spin 0 particle, whether it's massive or massive, is the same. It's always 1. That's why, if you have these quantum fluctuations in the vacuum, there is no reason whatsoever that you don't get an enormous contribution to the mass of the Higgs. And that can be substantiated. In the Standard Model of particle physics, we can't calculate the scale associated with the mass of the Higgs, or the W particle. That's not something, that's a parameter of the theory. So we have to just take it from experiment. But you can try to extend the Standard Model to deeper theories, more complete theories, where these numbers become calculable. In every example of a theory like that anyone has come up with over the last 30 years, you see exactly this fact. That if you get the Higgs, the Higgs has got to be accompanied by all kinds of other particles associated with that bigger theory. And you can't make it much, much lighter than everything else because exactly these fluctuations will just drag it up to the scale where all the rest of them are. Okay? Again, unless, once again, you do exactly the same kind of very ludicrous fine adjustments of the parameters of that theory that we just had to do to explain why there's a macroscopic universe. Okay, so this is another question. So here we have another kind of question, and we can go back to our menu of possibilities and see what might answer it. And there's only one thing left in the menu that we haven't used yet. Okay? So we had particles of spin 1/2, 1 and 2 that we'd seen before. The 0 just got used, that was the Higgs. The only thing that nature can do, compatible with general principles, that we have not yet seen it do, is exploit this possibility of having spin 3/2 particles. It turns out that the presence of spin 3/2 particles is possible, but it's only possible if there's a doubling of the number of particle species in the universe, and if you have this new symmetry, supersymmetry. So this is something that you've all heard about, very likely, but maybe not from this point of view. Okay? What's exciting about supersymmetry for most theoretical physicists is that it's the last thing nature can do compatible with these grand principles of spacetime and quantum mechanics that we have not yet seen it do. And it's quite remarkable that it is enough that it has the potential to solve this problem. All right, so I don't have time to explain how that works in detail, even as a cartoon, but maybe you've seen some of these things before. Maybe I will talk about another aspect of the problem, which is on everyone's minds right now. These ideas about supersymmetry, especially as a solution to the problem associated with the Higgs, have been around for 20, 30 years, and people have been anticipating supersymmetry for a long time. And we keep not discovering it at one accelerator after another. And we have not discovered it yet at the LHC. It's overdue. Okay? 20 years ago, even 20 years ago, it could have started showing up. This is not a situation where everyone thought things were awesome until 3 years ago, the LHC, and now everyone's nervous. That was already disquieting 10 years ago, 20 years ago. But it wasn't a disaster back then, and it's not yet a disaster with the idea now, but it's more and more disquieting. Okay? It's the 11th hour, no doubt. If this idea robustly solves this problem, it is the 11th hour for it. And one reason, one always elephant in the room that was also on everyone's mind the whole time is that supersymmetry by itself does not solve this problem associated with the cosmological constant either. And this question of why there's a big universe is obviously the much more leading question compared to the finer question of why gravity is so weak compared to all the other forces in this otherwise large world. So these were reasons to suspect that there might be something deeper missing about the way we are thinking about these problems. And well, we're going to get some more definitive answer about whether the simple pictures of supersymmetry that people were anticipating for 20 years, 30 years, are actually relevant for the Higgs problem at the LHC in the next couple of years. I would say that the status is that given what we knew even 10 years ago, what happened with the first run of the LHC was roughly compatible with what we expected already back then. In other words, many of us were already disquieted by its unappearance 10 years ago, and the fact that it didn't show up at the LHC is consistent with that. If we don't see it in the next 2 years, it's worse than that. Qualitatively, another order of magnitude worse than that. And so we really have to admit that this idea in its, this idea as a solution to the problem associated with the Higgs is not correct. Perhaps in much the same way that it has not been correct also for understanding the smallness of the vacuum energy. So I want to end by saying something about, this is all about theory. I want to end by saying something about experiment. So here I talked about two big questions, emergent space-time and why is there a macroscopic universe. And I didn't stress it, but it's even, as I mentioned, it's even possible these problems are related to each other. After all, you know, if we didn't get a macroscopic big space-time to begin with, we wouldn't wonder where space-time emerged from. Okay, so even being able to ask this question is somehow correlated with the fact that these solutions do exist with big flat universes, but then where did they come from? So they may be related to each other in a deeper way. But what's clear is that we're missing something. Even though we understand a lot about quantum mechanics and space-time, there's something huge that we don't understand about quantum mechanics of our relativistic vacuum. And now, there's many aspects of this problem. So one thing that we can do on the ones that are more closely related to experiment have to do with these questions about the expansion of the universe, the cosmological constant, on the one hand. There, our astronomer friends are planning to measure the acceleration of the universe more and more accurately to see whether it really looks like a cosmological constant or not. I think that's an extremely important and an exciting experimental program for them. But there's also an avatar of this problem having to do with the Higgs. And that gives a motivation in particle physics for the next round of experiments after the LHC. And something that a number of people are talking about now, both in Europe and in China, is the next big circular accelerator after the LHC, something that might be around 100 kilometers around. And this thing could, in the first phase, collide electrons and positrons and produce millions of Higgs particles to probe the properties of the Higgs, put it under a very powerful microscope and probe its properties more accurately. And then the next phase, collide protons at an energy around 7 times that of the LHC, around 100 TeV, and take us an order of magnitude deeper into the energy frontier. I think experimentally, the Higgs is the most important character in this mystery. It's the one thing we can get our hands on and study very, very closely. As I said, we've never seen an elementary particle like it. We've never seen an elementary spin-zero particle. And the reasons why we shouldn't have seen it are exactly these things associated with the violent quantum fluctuations and all this drama that we talked about is associated with the presence of this guy. And in fact, if at the LHC we don't see any friends associated with it, it heightens that drama. Okay? It's more and more mysterious that we've never seen. It's more and more unlike anything we've seen before. So, for instance, we will not know from the LHC. I told you that we see that it's point-like, but it'll still be a pretty fuzzy picture of how point-like it is. And even after the complete run of the LHC, no matter what we see, we'll have a picture that's sort of roughly like this. There would be some, if it was fully composite, it would have some natural size. It'll be more elementary than that. It'll be more point-like than that, but maybe by a factor of 5. Okay? So it's still a pretty fuzzy picture. So what you need to do is look at it, right? Really look at it to see how point-like it actually is. And looking at it involves banging, literally looking is banging photons into something. More generally in particle physics, it's again one of these 3-pronged interactions, which we can look at the Higgs with photons and Z particles and so on. But if you make millions of Higgs particles at one of these Higgs factories, you'll go from a picture like that to a picture like that. The resolution will increase by a factor of 30. And we'll really see if it looks genuinely point-like or not. So that's one thing. Now there's something else, another thing related to whether the Higgs looks point-like or not, which is not just does it look point-like to other particles, but does it look point-like to itself? Okay? And that's very interesting. It's associated, remember we talked about these basic 3-prong interactions. The most basic possible interaction is a 3-prong interaction of a single elementary particle with itself. We've never seen that interaction before in nature. Okay? Everything that we've seen, even things which we call self-interactions, like we say gluons self-interact or gravitons self-interact, there's always some quantum number which is changing for good reasons. Okay? We've never seen one elementary particle interact with itself. The most basic thing in the world. We've never seen it. That's because the only particle that can do it is the Higgs. Okay? And so you really need to see whether it interacts with itself, whether it looks point-like with itself, and to establish the presence of this fundamental interaction. And that's only something, you can't even do that at Higgs factory. To do that, you need to make 1 billion Higgs particles. So many of them that you can study and see this interaction. And that will happen at the 100 TeV collider. So at the LHC, we won't even know if this interaction is there. It'll be measured to 5% accuracy if you go to a 100 TeV collider. So these are the things that we'll learn for a fact from these machines. Okay, no extra speculation. Of course, a huge part of the excitement to go to 100 TeV is that it blasts into the energy frontier. Okay? And we keep going. We've been doing this kind of experiment for 100 years. There's absolutely no reason to stop doing it now. 100 TeV is not a crazy number. This is basically just 2 times higher than what we were thinking of doing 30 years ago with the superconducting supercollider. And it's pathetic if the human race can't do something 50 years after that, which doesn't just go up by a factor of 2. The technology's there. Nothing is obstructing it other than the presence of $10 billion. Okay? But doing that is going to probe, allows us to make particles with masses around 10 times higher than anything we can make at the LHC. And it allows us to probe these quantum fluctuations by something that improves the square of the energy of the machine 100 times more powerfully than we can do at the LHC. And this is very important. Again, you know, it's the quantum fluctuations of the vacuum that we don't understand. So we have to look at the vacuum and see what it looks like, and see what those quantum fluctuations look like. And this is the best way of doing it. All right. So what particle physicists love to see are pictures of the Earth with big rings on them. Okay? And if you see that, it means that some people are serious. And so here's a picture of the area around Geneva. There's the LHC. And this is the plans of our friends at CERN for what this next facility would look like. Okay? This is 80 kilometers around. It has to go under Lake Geneva. And so they're drawing these pictures. And our friends in China are also drawing these pictures on the ground. This is an area of 300 kilometers northeast of Beijing. That's a 50-kilometer ring. This is a 100-kilometer ring. And you can maybe fit a 150-kilometer ring there, too, if you squint a little bit. Okay? People tell me this is a beautiful area. The Communist Party officials hang out there for their summer vacation. There's no pollution. So it's not like Beijing, which is a horror. So, sorry? Actually, this turns out to be an amazingly good site for many, many reasons. It's not decided this is going to be the site, but it's one of the best sites geologically. It's incredibly stable geologically. Okay, so these people are thinking about it seriously. Okay? They're really thinking about it seriously. The plan in China, in particular, there's been a lot of work over the past couple of years to sort of push this case in China, partially because the Chinese government is coming out with its 5-year plan for the next budgetary 5-year plan for the next 5 years, and the Chinese physicists wanted to make sure that the R&D phase of this project is funded. So that's being decided on right now, but there's some very encouraging news just about 3 or 4 weeks ago. In the high-level summary of the 5-year plan, it ended by saying that China intended to host a major international scientific project, and on the same day, the state-controlled Chinese newspaper talked about the next big collider in China. Okay? So that the plans for a collider. And if it goes ahead as scheduled, they'll start digging in 2020 and maybe actually have the Higgs factory by the late 2020s. Okay? So, but anyway, this is still, there's a lot of hurdles still to go. There's a lot that still has to happen, but all the news so far is very, very encouraging. Now, final thing I'll say about it is, and this is what is often thought of as the obstruction, this costs 10 billion in your favorite units. Okay? So isn't this ridiculously expensive? Well, the world has lots of problems, lots of other problems. Do we need these toys for esoteric questions about about fundamental physics. And it's at the end of the colloquium now, so I don't have time to talk about all the great reasons to be doing this kind of science. But I'll say another aspect of it, which is that the amount of money that it costs is not large on the scale that these machines have always cost. And this is a nice way of thinking about it that Yifeng Wang in China likes to emphasize. That the amount of money these accelerators cost has always been, over time, over the past 40 years, roughly 10 to the minus 4 GDP. Okay? So the SSC, when it was canceled, was 10 to the minus 4 US GDP. The running cost of the LHC now is around 3 10 to the minus 4 European GDP. When China built its little 250-meter E plus E minus collider in 1984, it was 10 to the minus 4 China GDP in 1984. Okay? And the projected cost of these machines would be half 10 to the minus 4 for the Higgs factory and 1.5 10 to the minus 4 for the proton-proton collider in China. Okay? So this is the sort of thing human beings have done. And more far-thinking people in our past, like Tycho Brahe's boss, the king of Denmark, gave order 10% of his GDP to give Tycho Brahe this island so he could study the motion of the planets, right? And that 10% was an amazingly good use of this guy's money because, there's very few things of worth you can do in this life before you die. And that's one of them. And it's one of the things that survives and has some transcendent significance and we still talk about centuries later, right? So human beings do this, and there's nothing different now. And in fact, the scientific case is I think, incredibly strong for it. Stronger in many ways, because the scale of the question that we're asking isn't about details anymore. It's not about this or that particle. It's something sort of structural about our understanding of quantum mechanics, space-time, and the vacuum itself. Okay, so that's it. I just want to end by reiterating that something a lot of us in this field feel. It feels like a singular time in the development of fundamental physics. And it's because the questions that are on the table now are really deep ones. The underpinnings of space-time, the origins and fate of our macroscopic universe. And these are questions that people could have asked and did ask in one guise or another. You could have asked these questions 2,000 years ago. Okay? Bad time to ask about where did it all come from, what is space-time. You could have asked that. People did. Some, I shouldn't make fun of philosophers, but some people thought it was a good time to ask questions like that. It's not a good time to ask because there's zillions of other things you've got to understand before you do that. The number one rule of progress in science is not to ask the biggest question, but to ask the next question. The next question you can possibly make progress on. And so we have to do that. We understand a million other things. 100 years ago was the wrong time. 50 years ago was the wrong time. 30 years ago was the wrong time. But today, we're done most of the other questions. The ones that are left, the next questions are these ones. Okay? So now you can take that as a reason to be optimistic or pessimistic. It's like spending a long time to get to the base camp of Everest and finally you're like, fuck, now I have to climb that. Okay? And maybe you didn't bring the right tool. You don't have crampons. So now you're screwed. You got to go all the way back down and get crampons and come back up, or oxygen, lots of other stuff. But on the other hand, there it is. There is nothing else, right? I think that's incredibly exciting. To me, it's not only it's reason for tremendous excitement because we're finally dealing with those very questions that keep you up at night when you decide to get into physics. Just repeating what I said, the questions could have been meaningfully articulated even 50 years ago. But today, we have the theoretical framework that lets us properly pose them and gives us some definition of making progress on them or not, even purely internally, theoretically. And we also have fantastic experimental probes on a number of fronts. This would be a whole other set of colloquia to talk about all the other amazing experiments that are going on. But as I said, including now the exciting prospect of giant new colliders. So I'll just end by repeating that I think it's an exhilarating time to be doing this kind of physics. Just repeating what I said before, it's now the situation where the real next step is not going to be another little detail. It has to be progress on one of these big scale questions. But when that progress happens, someone will come and give a 45-minute talk about it because it'll be understood and you won't have to go through all this song and dance about what it might be. Thank you very much.
maybe a couple of questions, and then we can continue with wine and cheese.
This might be a dumb question, but you use the phrase emergent, emergent space-time, stable time, so I'm not quite sure exactly what that means.
Well, I mean it in the sense that let me be very, very precise. So we now know the world isn't deterministic, right? It's quantum mechanical. So even though the world isn't deterministic fundamentally, somehow there's an approximation in which it becomes effectively deterministic. The Newtonian picture emerges from the quantum mechanical one. Okay. Now that emergence is a lot more non-trivial because there's some qualitative change that takes place between one theory and the other. That's to be. I mean, if I'm answering your question a little more precisely, maybe than you meant it. But I want to make a distinction between that and something else, which is the transition between Galilean relativity and Lorentz invariance. Okay, there was a deformation. Okay, so now it's also important, but it's more mild, right? There was a relativity principle before. There's a relativity principle afterwards. There was some deformation of the existing thing. There's a parameter you just set to 0 or to infinity, and you move from one to the other. But there wasn't a discrete change in the logical structure from one to the other. So relativity was there throughout, just precisely how it was realized changes as you go from Galilean to Lorentzian. Whereas determinism is an epiphenomenon, is an emergent phenomenon. It's not really there. It's not part of the fundamental rules. For certain kinds of questions involving systems which can be separated into large parts that interact and decohere, you get things that look effectively deterministic. So the strong feeling is that space-time is going to emerge in a very similar way. And we see in these baby examples, like in the string theory particle physics correspondence, it's not like, a dumb thing that it could be is you go to very short scales and you see there's a graininess to space-time. Okay, that's an idiot idea. Okay, that's that there's some atoms of space-time. It's like the surface of this chair. It's an idiot idea because it violates Lorentz invariance. There's different. The atoms can't be small in all the frames simultaneously. And every idea like that would be more like Galilean to a Lorentzian. Every idea like that doesn't seem to work. But the ideas that do work are much more radical, much more interesting, right? In this string theory particle physics example, it's not like you had the inside and you just slightly mucked it up. There's no inside at all, right? There's just a thing that lives on the surface, and the inside is like a hologram encoded in some very interesting, non-trivial way. That's the sort of thing that we think is going to happen with space-time.
You're talking about perhaps something more than just like a low energy or.
Oh, absolutely, exactly. Yes. So again, it's more like the example when we go from classical to a quantum, right? So there's something much more structurally different between the theories. And that's why, as great as Einstein was, and we celebrate the 100th anniversary of GR this year, relativity is something that could be come up with one genius thinking about things for 10 years. Quantum mechanics took 15 people 25 years working very hard. It's a completely different animal. Right?
So the standard model has two relevant operators, which is the CC and the Higgs mass squared, and we compute them both and they're spectacularly wrong. So do you think it's likely that there's a common resolution and we could connect to your ideas of extending space-time and quantum mechanics?
Well, one hopes that they might be related to each other. Of course, as you know very well, you can use examples from the history of physics to illustrate any polemical point you want. I'm very good at this. So indeed, you could say we'll someday realize that these problems were connected to each other, and we'll look like such fools for ignoring the cosmological constant all this time and focusing on the hierarchy problem. What idiots they were. How could they ignore this elephant in the room? Okay, but if we go back 40 years to understanding why the charged pion was not so much heavier than the neutral pion, which is a perfect cousin of the hierarchy problem, as you know, then you could have been a very learned, sophisticated theorist back then and said, how dare we work on this pion problem when we don't understand the cosmological constant problem? And you would have been an idiot then. Okay? The problem is that we never know when we're idiots. Chances are we are. And that's just the price of doing business. But I think we'll know a lot better in 3 years. We'll know a lot better. Actually, we'll know even much better in 30. But certainly if we don't see any hints of new natural physics at the LHC, of course it becomes much more tempting to try to relate the problems to each other. In the multiversian picture of the world that I didn't talk about at all here, it's plausible that the problems are connected to each other. But I think it's also plausible that there's elements of that picture that are right and elements that are being badly misinterpreted, and that in the correct interpretation, the problems will be related, and will be related to the emergence of space-time. As I said already, it's not at least the cosmological constant problem and the emergence of space-time question are not disconnected from each other. And in fact, in most other approaches to quantum gravity that don't get anywhere, one of the reasons they don't get anywhere is just to start with, you don't get a space-time to talk about, right? And so, but if we don't have supersymmetry, if we don't have something that lets us control the cosmological constant, and no approach we know, any approach we know, do we get a big space-time to begin with. So sometimes you need a big space-time to begin with to have the emergent space-time problem to talk about. So that's why it's not implausible to me that the questions are related to each other.
So we can keep asking Nima questions over wine and cheese in the 6th floor.